All right. Hi, everybody. Thanks for tuning in today. So this week, our seminar speaker is Dr. Brad Foley, who is currently an associate professor at Penn State University. Dr. Foley is a geodynamicist, which just means he's really interested in the interior dynamics of planetary bodies, in particular thinking about what causes plate tectonics, sort of its history on Earth, and then whether it actually exists on other planetary bodies, and even including other solar systems. And then among other research topics, he also thinks about how the dynamics of planetary interiors may affect the habitability of exoplanets, which he'll be talking about today. And for most of his work, he uses different types of theoretical and numerical models and collaborates with researchers in other fields to sort of put his work into broader context. Dr. Foley earned a bachelor's degree in geological sciences from the University of Southern California and a master's and PhD in geology and geophysics from Yale University. He then went to Carnegie to do a postdoc for 2 years and then started his current position at Penn State. And so thank you again, Dr. Foley, for taking the time to talk with us. Take it away. Thanks again.
Great. Yeah, thanks for having me. Fun to visit with you guys virtually, at least, right? From similarly rainy and dreary Pennsylvania, right? Yeah. So, like Francis said, the great introduction there. One of the big things I'm really interested in when it comes to exoplanets is how the interior dynamics of a planet and its interior evolution affects volatile cycling, the surface environment, climate evolution, all things we can kind of wrap up into thinking about the habitability of exoplanets, right? So that's a main topic I'll talk about today. And I'm going to hit this in a few different ways. I'm going to talk about the role of tectonics and in particular focus on the potential for habitability on planets that don't have plate tectonics like Earth does. And I'll explain why I think it's important to consider planets that don't have plate tectonics. Then I'll look a little bit about how long planets, again, that don't have plate tectonics are in a, as I'll define, a stagnant-lid regime, could potentially remain volcanically active and drive the kinds of geochemical volatile cycling that might be really important for habitability and what implications that has for searching for exoplanets. And then hopefully if I've got a little time at the end, I'll talk about related, but a little bit of a different kind of gear shift project on the role of surface exposed land and whether it's necessary for land to be exposed at the surface to drive weathering and climate feedbacks related with the carbonate silicate cycle, or whether this can happen on totally ocean-covered planets. Right? Okay, so to start off, we should first talk about what are the kind of ingredients to make a habitable planet. And this is probably the scariest thing for myself as a geophysicist to start off with, because now I've got to talk about what does life and biology need, right? So for my very simple geophysicist understanding of what is important for Earth-like life to develop on a planet. I've kind of come up with this short, probably incomplete, but at least a good guide list, right? So there's thoughts that we need liquid water to serve as this solvent for life. Of course, there's ideas about using other kinds of solvents, but the life we know of, right, is using liquid water. We know from life on Earth that there's some sort of temperature range that seems to be required for life to be able to thrive and reproduce, going down to there's a lower limit and an upper limit based on experiments and looking at extremophiles, and also ideas about essential elements, bioessential elements like the SNOPs, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur elements that we think are essential for life to be able to do its thing, right? So we need some way to get these in enough abundances into oceans or some sort of environment that life can take advantage of it. So we'll be going through and using some of these guides to then see how these link to the interior state and interior evolution of planets. To kind of place some broader scale views of like what kind of characteristics does a planet need to have to be able to satisfy these constraints for life to be able to develop. An important caveat for this is whether we think these conditions need to be met on a planet's surface or whether environments like a subsurface ocean might work as well. So in principle, there doesn't seem to be any reason why these conditions I laid out earlier about liquid water and a suitable temperature range and these bioessential elements needs to be directly at a planet's surface. And of course, there's a lot of astrobiological interest in icy moons in the outer solar system, like Europa and Enceladus, that have a frozen ice shell, but potentially liquid water oceans beneath that. So these, of course, also could be good environments for life. I'm going to not focus on these types of situations in my talk and instead focus on planets where we can meet these conditions for life at the surfaces. And that's not because I don't think it's not feasible on other types of planets, but when we think about trying to potentially remotely detect biosignatures on exoplanets, it's probably going to be easier if the life we're looking for is living on the surface, right? So I'll focus on surface life in the talk from now on. But don't take that as me thinking that life beneath surface ice-covered planets is not feasible. All right, so how do we translate some of these requirements we laid out into more kind of like physical characteristics of the planet? The first two, talking about liquid water and a suitable temperature, a climate range, are related to what's controlling the planet's climate state. Right, and that's of course affected by a number of things, but some of the main ones are, kind of the first order, the stellar radiation environment, right, the energy the planet's receiving from the sun, but also when we think about the kind of planetary geological dynamics, geochemical cycling processes that I'll get into that we think are really important for regulating a planet's climate, right? And then of course, for looking at bioessential elements, getting into surface environments where life can use them. These same kind of geochemical cycles are really important for those as well, right? And these geochemical cycles that I talked to are linked to a planet's interior dynamics, interior evolution. So we'll see how, I'll touch on some of those ways they interact with each other and place constraints on the kind of characteristics of planets that are important for driving their habitability, right? Okay, so to start off in thinking about how planets can meet these characteristics for life, I feel like you always pretty much have to start with this idea of the habitable zone, right? And so this is looking at the range of solar radiation that planets are receiving that we think is kind of just right for the planet to be able to host liquid water on its surface. Okay? And so the basic idea here is we've got different boundaries. There are a few different lines here looking at kind of different assumptions about how these models are made. But the punchline kind of first order takeaway is that we've got an idea that there's some inner boundary where you can be too close to the star you orbit, where basically just the stellar radiation you're receiving is too high to ever allow liquid water oceans to form. And that's actually without any other greenhouse gases. You find this radiation limit with a purely water vapor atmosphere. Basically, water would never be able to condense into liquid water and always stay as steam and then potentially escape and lead us to something like we think happened on Venus. Right? And then the outer edge is the limit where planets are too cold. And the idea here, at least in the classic habitable zone that my now recently retired colleague at Penn State, Jim Casting, really pioneered for many years, is this idea that actually there's a limit to how much warming you can do with CO2 in a planet's atmosphere. And at some point, putting more and more CO2 in the atmosphere actually doesn't warm it anymore. It actually starts to cool the planet off. And that's because it starts scattering incoming sunlight away more than it leads to greenhouse warming, right? So this outer limit and the classical habitable zone from Casting setup is the limit where no amount of CO2 in the atmosphere can keep the climate warm anymore, right? It turns out there's other gases like adding hydrogen to the atmosphere can probably push this limit out. So I don't think you should think of the outer edge of the habitable zone as being like a really fixed limit. But at some point, there's probably too little radiation coming into the planet for it to be able to remain above freezing. Okay, so this habitable zone lays out like a great kind of conceptual framework, right, for thinking about where planets need to be to potentially be habitable, but it's not enough on its own. It's really not nearly enough on its own, right? So a planet sitting in this habitable zone, right, if a planet's sitting really close to the inner edge, right, like this arrow I drew here, right, that planet is going to need to have a low amount of greenhouse warming for it to still have a temperate climate, because it's still receiving a lot of sunlight, right? Not so much that it would, kind of be guaranteed to cause all the water to evaporate, but we could still get into climates that are too hot for life if we don't have, the right amount of greenhouse warming, right? And likewise, if you think about a planet really close to the outer edge of the habitable zone, maybe sitting out here, right? That's a planet that would need a really strong greenhouse effect for it to stay above freezing, right? If you took Earth and moved it out towards Mars and kept our greenhouse effect the same, right, we would freeze over, right? So for planets to actually be habitable across this whole habitable zone, right, they need actually some sort of mechanism, right, that's allowing the amount of greenhouse warming to change as a function of the sunlight the planet's receiving, right? And we think we have a good idea of what that is, right, at least based on how we think Earth has worked, right? And that's this idea of the carbonate silicate cycle, right? So the carbonate silicate cycle is the cycling of CO2 from the atmosphere to the rocks, right, through weathering of silicate rocks on land and the formation of carbonate minerals on the seafloor, right? And then these carbonate minerals ride subducting plates, right, down into the mantle interior, recycle carbon into the interior. Some of this gets outgassed right away at arc volcanoes, right, or eventually makes its way back out plumes or ridges. Right. And so we've got a rate at which CO2 is being put back into the atmosphere from volcanism and a rate at which CO2 is being taken out of the atmosphere by silicate weathering. Right. And this can stabilize climate because there's a nice feedback, a negative feedback, where the weathering rates, right, are sensitive to climate. So when climate gets warm, weathering rates go up, and that tries to return the system back to a more kind of stable state. Right? And so a good illustration of how this works is this nice simple figure here, right, which allows climate regulation as a function of incoming solar luminosity, right? So this is the solar energy relative to the Earth received today, which would be 1, right? And so thanks to these stabilizing feedbacks in the carbonate silicate cycle, if you have lower amounts of solar energy reaching a planet like the Earth, right, these feedbacks naturally, right, work to put more CO2 in the atmosphere and make the climate above freezing, right? At least warmer than it would have been without these feedbacks active, right? And then as you move, say, outwards in the habitable zone, or sorry, I should say move inwards in the habitable zone towards the star, right, and are receiving more sunlight, right? Or you can also think of this as an evolution in time, as our sun has increased in brightness over time, right? And the incoming solar energy increases. These same feedbacks work to draw CO2 out of the atmosphere, right? The climate's still going to warm up, but not as much as it would for a case where there was where these feedbacks weren't active, right? Which is what this dashed line is showing, right? They can jump up into temperatures that would be not habitable for life and would potentially cause lots of water loss from the planet, much more easily than with the carbonate silicate cycle active, right? So we think this is kind of the key thing that allows for habitability for planets throughout this habitable zone, right? But it's really important to then consider, can we rely on this always happening, right? Is this, a really kind of like perfectly tuned feedback loop, or are there ways this feedback can fail, right? And then if there are ways this feedback can fail, how are those connected to the kinds of characteristics of the planet and its interior state and dynamics and evolution, right? And that's really the main thing I'm going to focus on, right? And so yes, there are ways this feedback can fail. And this figure is showing some nice examples of that, right? So here, this is plotting climate states, incorporating the carbonate silicate cycle feedbacks as a function of CO2 degassing rate from volcanoes, right? This is normalized to present day Earth. So 1 is present day Earth going higher or lower, right? And then as a function again of the incoming solar flux normalized to present day Earth, right? So, there's a kind of region of space with low solar flux and lower degassing rates, where even with these feedbacks trying to be active, right, it's not enough to keep the climate warm and the planet would freeze over, right? So basically too little volcanic outgassing of CO2, right? Planets can get too cold and they can freeze over, right? Then there's a, kind of Goldilocks zone where things work just right and keep the climate warm. And then it's not drawn in this figure, but I've worked out limits, and I'll talk about these as I apply this to different types of planets throughout the talk. There's a limit where you can have too much outgassing, where CO2 is being released to the atmosphere so quickly from volcanism, right? Or there's some other kind of process that's limiting the rate at which CO2 can be taken out of the atmosphere by weathering, right? That basically the CO2 release from volcanoes swamps, it overwhelms what silicate weathering can do. And a bunch of CO2 builds up in the atmosphere and the planet gets really hot, sort of like a Venus type hothouse scenario, right? So there's ways this feedback can fail, right? And these ways these feedback can fail are in large part tied to the interior dynamics of the planet that's dictating long-term volcanic outgassing rates, long-term rates of volcanism and creation of fresh rock on the surface and tectonic process. All right, so I'll talk about 3 main parts of this, right? So here are the kind of 3 main goals of the talk, right? So the first one is looking at whether these same feedbacks in the carbonate silicate cycle that help regulate climate can operate on a planet without plate tectonics, right? The way I describe this, and we always draw that this carbonate silicate cycle for Earth is intrinsically tied in to the operation of plate tectonics on Earth, right? So it's a big question about whether this works on planets that don't have plate tectonics, right? Then related to that, we'll get into looking at how long potentially habitable climates can last on planets that don't have plate tectonics, right? And I'll use a series of thermal evolution models and actually tie this into constraints on the radioactive heat budgets that exoplanets might have based on looking at compositions of stars, right? To place some minimum bound, kind of most conservative constraints on how long volcanism and geochemical cycling can last, right? And then the last part I'll try to hopefully get to will be looking at the case of, what happens when we have a water world or aquaplanet where maybe we don't have continents or the water level is so high it's flooded the surface, right? And whether these same kind of feedbacks can work in that case. Right? Okay, and to acknowledge some collaborators on this. So the first part that I'll talk about in terms of different tectonics, I got some great collaboration with one of my colleagues here at Penn State, Andy Smyth, who's actually a metamorphic petrologist, right? And he was really key in us being able to figure out how carbon would cycle from the atmosphere back into the crust on planets with stagnant lids. Then for the middle part of the talk, Cayman Unterborn, someone I've collaborated with a lot on looking at exoplanet evolution, right? And here's really key in helping pair these thermal evolution models I'll show with abundance constraints on heat budgets of rocky planets from stars. And then the last part is work that a recent PhD alum of our department, Ben Hayworth, worked on with me. All right, so to lead into talking about this first major topic, which is whether the carbonate silicate cycle can work and regulate climate on planets that don't have plate tectonics, I think it's worth laying out, why should we even care about this, right? So if we look at our solar system, right, it turns out that all of our neighbors in the solar system, and actually any rocky body basically that we know of outside of the Earth, does not seem to have plate tectonics, at least global scale, full network of moving plates the way Earth does, right? And most of these planets, in particular Mars, Venus actually might be kind of an in-between case, right? But Mars seems to be in what we think is the very extreme, opposite end member to plate tectonics, something we call a stagnant lid, right? And that's a planet where the surface, right, you can think of as being made up of just one big plate everywhere that covers the whole surface, right? This, one big plate is rigid, right? And so convection in the mantle is just taking place beneath this one plate, right? And so we don't have any movement of individual plates colliding or subducting on Mars compared to Earth, right? And so that's the characteristic of stagnant lid planets versus planets with plate tectonics, right? So we know these other types of tectonic regimes exist. We also know that they seem to maybe be more common than plate tectonics. We really only have this one planet we know of that has plate tectonics. Right, and also, based on, I've actually worked a lot on this problem of, what is the geodynamics that leads to plate tectonics on Earth versus the other planet versus, the other planets in our solar system, and tried to make predictions about exoplanets. But basically, our understanding of what causes plate tectonics is not advanced enough for us to be able to make a confident prediction about exoplanets, right? So basically, when we think about exoplanets, we really need to consider whether they might be habitable in regimes other than plate tectonics, right? In particular, stagnant lid being the opposite end member is a key one to consider, right? So I was really interested in working on this, right? And I worked on this a few years ago. So I'll kind of summarize those results and how that leads into the next part, right? So I wanted to look at how would carbon cycle on a planet that doesn't have subduction to return carbon to the mantle, right? So on a planet without plate tectonics and a stagnant lid regime, right, these planets do still have volcanism, right? So there's certainly throughout Mars's history been volcanism, although it might die out more easily than it does on a plate tectonic planet, right? So there's convection in the mantle driving volcanism, and that's going to outgas interior volatiles like carbon, this is the form of CO2, right, or other carbon species to the atmosphere, right? And then the idea of this is, I wanted to think about planets that are already in their habitable zone, right? So they could potentially have liquid water on their surface, and do these same kind of feedbacks that we think help regulate climate on Earth as we sit in our habitable zone of our sun, would they operate on these other hypothetical planets, right? So we're going to consider stagnant-lid planets that have liquid water, right? So weathering can potentially happen, right? And see whether the feedbacks in the carbonate silicate cycle can still work based on limits like the amount of CO2 outgassing and the amount of fresh rock we're forming at the surface, right? All right, so with that assumption, right, that means we could imagine CO2 that's being outgassed by the mantle weathering out, right, and forming carbonate minerals in the crust, right, and being deposited into a crustal reservoir, right? And then since we don't have subduction, right, the only way this material could potentially get returned to the interior is by just later lava flows piling up and basically just pushing the crust down, right? Which is something we think can happen on stagnant-lid planets. And it definitely looks like it happens in a really extreme case in Io, right? Right, so as this crust gets buried down, you can imagine like a layer of carbonate that first forms at some point in time on the surface of this planet, and then it gets buried down by later lava flows, right? It potentially could get buried so deep within the lithosphere, right, that it eventually can founder, can drip down, right, into the convecting mantle below and potentially return carbon to the mantle that way, right? Or another thing that could happen, and this is where my metamorphic petrology colleague really helped, right? And we found actually this was the primary thing that happened, is as this carbonate minerals are being buried through the crust, they might just heat up, get to high enough temperature and pressure conditions where they metamorphically decarbonate and release their CO2 back to the atmosphere as a metamorphic outgassing flux on top of an outgassing flux coming from volcanism, right? Okay, so we've developed a model to incorporate these processes. And I basically was asking two main things. So I was looking at like two potential limits of where the carbonate silicate cycle could break on such a planet, right? And one would be if the outgassing rates of CO2, both from volcanism and metamorphism, are those high enough, right, to keep the planet warm, right, based on some simple climate models of how much CO2 we need, right? And then the other big end member is whether we reach this other limit where CO2 outgassing is overwhelming what weathering can do, right? And so that can be calculated in this idea called the weathering supply limit, where you basically imagine all of the fresh rock that you're bringing to the surface through tectonics or through volcanism gets immediately weathered, right? And if that supply, kind of that provides basically like an upper bound on how high can the weathering rate get. If that upper bound is lower than the outgassing rate, right, well, then we're just going to keep piling CO2 up in the atmosphere, right? So for stagnant-lid planets, I calculated this limit based on the rate at which volcanism is producing fresh rock at the surface that can be weathered, right? So I'm going to look at both limits and see when we can fall, in the sweet spot and have habitable climates. Okay, so I built these models using kind of standard tool in geodynamics called thermal evolution modeling. And I'll use this for this part of the talk and also the second part, right? So the idea here is we can picture the mantle like a box, right? In this box, we just look at having, a heat input, a heat flux coming in from the core, right? And then a heat output, which is the heat flux from mantle convection that's being released through the lithosphere up to the surface to the atmosphere and space, right? So we've got those fluxes coming in and out of the box. And then of course we have radioactive element providing heating in the interior, right? And so we can just set up a very simple energy balance and say that the change in the mantle energy, right, within this box, right, is related to the heat being produced internally, the heat coming in from the core, and then the heat leaving out through the surface, right? So if you turn that into a form of equations, it looks like this, right? So here's and this can be then turned into an equation giving us the rate of change of mantle temperature, where this is, you should think of as like the volume average temperature within this box representing the mantle, right? Right, so the rate of change of that temperature being balanced by, again, heat production, heat coming in from the core, right, and heat being lost to the surface by the heat flux due to convection in the mantle. Right, the real kind of trick of this is figuring out how to write an equation for these heat fluxes, right? And actually in this modeling I'm going to present, I'm going to assume that the core heat flux is negligible. So we're basically going to cross that out. That's, the core heat flux is probably smaller than radioactive heating and heat loss from the surface on Earth. It's not necessarily exactly negligible, but doing this just makes the system like much simpler to work with and understand. So it's a reasonable approximation for looking at the kind of conditions on exoplanets we're going to do. All right, so that leaves me with worrying about the surface heat flux, right? And this is another really classic topic in geodynamics that lots of people have worked on for many years, and that's trying to determine scaling relationships, simple little parameterizations, almost like little rules of thumb that relate usually the Rayleigh number describing the convective vigor of the system to the heat flux that convective system will release through its surface, right? And so based on a number of scaling laws and lab experiments and theory, right, we worked out kind of the general idea that the higher the mantle temperature is, the more vigorous its convection is, and the higher the heat flux will be. And that's because more vigorous convection, right, will set up a thinner thermal boundary layer, right? So this is a kind of typical temperature structure in a convecting fluid. And this top part where the temperature starts to go down to match the top boundary condition is the thermal boundary layer, right? And this sets the heat flux coming out of the convecting mantle up to the lithosphere out to the surface, right? So the more the vigorous convection is, right, the thinner these boundary layers get, that creates a higher geothermal gradient, right, and a higher heat flux, right? And so we're going to use parameterizations that describe that behavior in these models. All right, so this is a good example of one of these thermal evolution models, right? So thanks to these relationship between mantle temperature and convective vigor and heat loss, this results in a kind of characteristic type of behavior to how we think planets cool off for the most part, where when they start really warm, right, their temperature drops very rapidly at first, right, because they're losing heat really quickly. And then as they cool off, right, their rate of heat loss declines because the heat flux gets lower, and then they cool more gradually after that, right? So this is an example of the temperature evolution over a few billion years from one of these models. I then looked at outgassing of CO2, right, and how it moved from the mantle to the crust. So I started assuming that all the carbon is in the mantle and then gets outgassed, right? And I looked at whether this outgassed carbon that gets deposited in the crust can ever be recycled back into the mantle or not, right? And what we found is that basically always, right, carbonated crust being buried would heat up so much that it would break down the carbonated minerals and release CO2 back to the atmosphere well before it could get deep enough to recycle back into the mantle, right? So this leads to actually a long-term depletion of carbon from the mantle into the crust, right? So these are the CO2 reservoirs over time. We start off outgassing carbon from the mantle, and it just drops and drops over time as this carbon builds up in the crust, right? And then carbon in the crust is just gonna start recycling, right? So it gets buried down to a depth where it breaks down and gets released to the atmosphere, goes back to the atmosphere, drives more weathering, gets back into the crust. And as long as volcanism is active, right, we end up just kind of recycling carbon through the crust, right? So this leads to CO2 outgassing fluxes, right? So the dashed line here is the volcanic release from the mantle of CO2. It starts off high, you can't really see here, but drops pretty quickly, right? And then the dot dashed line, which is underneath the blue line, right, stays much higher for most of the evolution. That's this metamorphic release of CO2 to the atmosphere, right? And then the total, which is the sum of the two, which is the blue line, right? You see mainly it just follows the metamorphic outgassing flux because that's the dominant player. Right, so I ran a bunch of models like this in different parameter space, right? And the two parameters that seemed to be most important were what I was calling the total budget of carbon in the mantle, right? So I'm assuming the mantle has some amount of essentially CO2 available to be outgassed, right? And I'm calculating that in terms of the total amount of moles, right? Earth, we think, is around 10 to the 22 moles of CO2 available to be outgassed CO2 in the mantle, right? So I varied a few orders of magnitude on either side of that. Right, and then the other really important component in these is the heat budget of the planet. So I'm plotting this as a heating rate in terawatts of radioactive heat production at the planet's birth. So like time zero for the planet, and then it decays over time radioactively as a result of the radioactive elements that make up this heat budget. Right, and so I took these models, in this kind of grid space, and I calculated the thermal evolution, like I just showed the example of. Right, and then I mapped out, what the outgassing rates were over time and whether that led to habitable climate conditions or not, right? And then calculated this lifetime of habitable climates in billions of years, right? So that's what the contour lines and the colors are showing, right? And you can see a few limits here, right? So on the left side of the plot, right, for very low carbon budgets. These are planets where even if they have lots of volcanism, if they have, say, lots of heating power, right, they'll have lots of volcanism and stay volcanically active longer. There's so little carbon in the interior available to be outgassed that even lots of volcanism leads to a low CO2 outgassing rate. And so these planets just stay too cold their whole lifetime, right? So these planets would basically be like frozen over, right, their whole life, right? The other side of that is where we hit this weathering supply limit, right? So now there's so much carbon in the mantle that as we outgas this carbon through volcanism, right, it's more than silicate weathering can take down, even if we entirely carbonate, all the essentially basaltic rock we're forming at the surface from volcanism, right? So this leads to a limit where CO2 builds up rapidly in the atmosphere and we go to a hothouse climate, right? So the planets over here, right, where you see the blue, their habitable climate lifetimes are basically 0 because they get way too hot really quickly, right? And then of course we've got some Goldilocks zone in the middle, right, where things are just right for the climate to stay habitable for a few billion years, right? And the larger the heat production, right, the longer this cycling process driven by volcanism can last, and so the longer we think habitable climates can last. One important caveat I'll just mention here is, it's actually not that clear to me, or I think most people who would work on a problem like this, like just what would happen to one of these planets when volcanism dies out, whether the amount of CO2 in the atmosphere would kind of get locked in and it might be able to remain habitable for some time after that. To be conservative, I assume that when volcanism died out, the planet would lose its ability to regulate climate and lose its ability to maintain a temperate habitable climate. So I assume habitability basically ends when volcanism ends, but it's possible it might last a little longer than what I'm modeling here. All right, so that leaves open a couple of important questions that motivate the next part of the talk. And that's, this type of modeling was very parametric. I'm just kind of varying things as free parameters, right? So it's important to think about like how likely are planets to actually fall within this sweet spot, right? Can we constrain some of these, parameter like carbon or heat budgets to give us an idea of, which planets might, map into the zone where they could have long-lived habitability, right? So the carbon budget, right, from my perspective, at least right now, is probably really hard to constrain, in part because it's certainly not directly measurable for any known exoplanets. It's even kind of hard to infer for the Earth, right? And it's also something that even if we tried to look at the composition of stars or planetary, protoplanetary disks or things like that, which I'll use actually to talk about heat budgets, it's a volatile element, so it's not clear that what we see in stars or in disks is going to match what actually ends up in the planets, right? So carbon budget we probably have to keep as relatively unconstrained right now, but the heat budget should be better constrained, right? So the heat producing elements are more refractory, right? And we can have better confidence that what we see maybe in stars or in disk materials is going to reflect what's going to be in the planets, right? So that's the next step we're going to do, is try to constrain the heat budget by looking at the composition of stars. Right, so this is where I then teamed up with Cayman Unterborn, who's worked on some of this over the years, and looking at stellar abundances to try to infer properties of planets. Right, so he helped us pull stellar abundance measurements for the main long-lived heat-producing elements from a major catalog of stellar composition measurements called the Hypatia catalog. Right, and this is the result of what we find. Right, so we looked at thorium abundances. Right, so thorium being one of the major long-lived heat-producing elements. Right, potassium abundance for potassium-40. Right, and then this is europium, which is used as a stand-in for uranium. Right, so of course uranium is the other major long-lived heat-producing element. But uranium is actually really hard to measure in stars due to, it's actually like kind of beyond my astronomy knowledge, but there's like another spectral line that masks it, and so they can't see it very well. But europium is thought to be a really good proxy because it forms through the same nucleosynthesis processes as uranium. Right? Okay, so these give us some idea of what the variation of these heat-producing elements in other stars, which we can assume is, hopefully matched fairly well between the stars to the planetary formation environment and planets that might be orbiting these stars. Right, so we use these histograms here, right, as representing essentially the kind of random planetary system to planetary system variation in each of the major heat-producing elements, thorium, uranium, and potassium, that planets might have, right? So basically what we're going to do is we're going to use these histograms, and we fit log normal distributions to them, because that was the type of distribution that fit the best, right? And treat that as, a kind of random input to a set of similar kinds of thermal evolution models, right? To look at how long volcanism and potentially habitable climates can last in models driven by these probability distributions for heat-producing elements, right? And just for completeness sake, I'll also mention that the same sets of models, we're also going to take other key input parameters. So other key input parameters in modeling a planet's thermal evolution are the initial temperature of the mantle, right? This is, of course, it's not constrained for Earth. It's definitely not constrained for exoplanets. So we just used a reasonable range of values that's been used in past models, and that should say 2000 Kelvin, not 200 Kelvin. So 1700 to 2000 Kelvin is a reasonable starting range, right? So we'll just vary that uniformly, and we're also going to vary the viscosity of the mantle uniformly, right? And this viscosity I'm listing is something we call a reference viscosity. That's the viscosity the mantle would have if it was at the same temperature as Earth's present-day mantle is, right? And there has still been a strong temperature dependence in the models to the viscosity, right? Warmer temperatures, the viscosity is lower. All right, so when we take this set of models, right, and sample from these distributions of heat-producing elements and also the uniform distributions of other key input parameters, right, we find this spread of how long volcanism can last on planets, assuming stagnant-lid tectonics, like we've been doing before, and also looking at variations in planet mass, right? So there's a large spread, right, in lifetimes of volcanism, upwards of 1 to 2 billion years, right, away from an average in the middle. And this spread is determined largely by the variations in heat-producing element budgets, right? So a planet that lucked out and got a bunch of potassium or uranium or thorium versus one that unlucked out, I guess you would say, and got very little, right? And also the range of viscosities, right? So higher viscosities lead to longer-lived volcanism because the planet stays warmer longer, right? We also see an effect of, as the planets get larger, right? And this is sort of a kind of standard result. The larger planets, the easier they hold on to their heat, so they tend to stay warmer and volcanically active longer as well. Right, some other important factors here. So I talked about varying viscosity, right, and heat budget, right? And things sort of work the way we would expect for these thermal evolution models, right? So the higher a planet's viscosity is, right, that's going to slow its cooling rate. And so that tends to keep the planet warmer for longer, right? So we tend to see higher lifetimes of volcanism or degassing as viscosity increases, right? So going from reds to oranges or yellows is leading to longer lifetimes of volcanism, right? And then of course, the larger the heat budget the planet acquires, right? And so this is being mapped out as an initial heat budget, right, relative to an Earth-like planet with the same amount of uranium, potassium, and thorium that Earth acquired, that's heat budget, right? So as you go to higher values of that, right, due to, just lucking into acquiring more of that during formation, then we also get to longer degassing lifetimes, right? So high viscosity and lots of heat-producing elements is the way to have long-lived volcanism on a stagnant-lid planet. All right, so, that's all well and good for thinking about these variations in heat-producing element budget that we see in stars that we interpreted as, again, representing just the kind of random system-to-system variation that might be characteristic of planets throughout our galaxy. Right, but there's another important aspect of variation in planetary compositions, right? And that's long-term trends due to galactic chemical evolution, right? And the galactic chemical evolution basically comes from the way elements are being produced through nucleosynthesis in stars and then distributed throughout the galaxy, right? So we want to take that into account as well, right? Not just the kind of variability you might find in planets being born today, but how do these trends change as you go back in time, right? So we used models developed by Elizabeth Frank, who worked out the galactic chemical evolution of these four major heat-producing elements, potassium, both types of uranium and thorium, right? And the general punchline is that for most of them, it's thought that the abundances were higher early on in galactic history, right? And just to orient yourself on these figures, now that I'm talking about galactic chemical evolution, 0 here means time 0 for the Milky Way galaxy. So that's when the Milky Way formed, not when the Earth formed. Earth formed about 8 billion years after the Milky Way formed, so 8 here is when the Earth forms. Right, so the general thought is that these heat-producing elements mostly decayed over time, and that's, I think, primarily because of them being diluted in larger amounts of heat-producing, or sorry, not heat-producing elements, rock-forming elements like magnesium and silica were increasing in abundance over time. And so, if you think about a planet acquiring these heat-producing elements, we have to think about the concentration of these in the actual, rocks that the planet makes in the end. Right, so the concentration we'd expect in mantles declines, except potassium, which has this kind of funky behavior where it increases a little bit and then drops down. Right, and so based on this, we can then look at the breakdown of planetary heat budgets at different times during galactic chemical evolution, right, and which elements seem to be most important for making up the planet's kind of initial heating budget. Right, and so these plots, mainly looking at the colored ones, are showing you an example of an initial heat budget of a planet, then broken down to the different heat-producing elements that make that up. And green here is uranium-235, right? Yellow is potassium, and then blue and red are thorium and uranium-238. Right, so there's a shift where planets formed very early in galactic history because of galactic chemical evolution. Their heat budgets tend to be dominated by uranium-235, right? That's the biggest kind of component making up their heat budgets, right? And their total heating rates in terms of terawatts tend to be higher because of these elements having a little bit higher abundance, right? But uranium-235 has a short half-life, so we didn't get that much bang for our buck from that, right? Having more uranium-235, yeah, that helps keep volcanism active a little longer, but not that much longer, right? And then as the galactic chemical evolution trends evolve more towards the time when Earth formed, right, then we see the initial heat budget being dominated by potassium, right? Potassium had a really wide spread among the stellar compositions. So that seems to be the element that has the biggest control over where the planets, randomly acquire from these distributions, large initial heat budgets or smaller initial heat budgets, right? So potassium abundance for the later formed planets tends to be what really controls their degassing lifetime. All right, so we took all this together. So we treated the these log normal distributions that I showed at the start as representing some kind of constant variability in the heat producing elements throughout the solar system, throughout the galaxy, right? And then we take into account galactic chemical evolution. We changed the median or the average of those distributions to match the galactic chemical evolution trends I showed a couple of slides ago, right? So basically, a planet born at the start of the Milky Way versus one today would have slightly different distributions of the heat producing elements to draw from, right? So we ran really huge sets of models, right? So we modeled big Monte Carlo sets of models, sampling from all the parameters for planets of different sizes and different formation ages, right? From when Earth formed to much earlier in galactic chemical evolution up to today, right? And we use this to map out how long planets stay volcanically active as a result of these changing heat budgets, both from random kind of system to system variation and also from galactic chemical evolution trends, right? And then what we're showing here is the average degassing lifetime we get in the middle, right, compared to the lower bound, right? So just remember that blue band I showed earlier. So the bottom of the blue band, right, the middle of it, and then the upper level of that blue band, right, now is a function of when in galactic history of the planet forms, right, and the size of the planet on the y-axis, right? So planets formed earlier in galactic history, right, tend to have larger heat budgets, right, because of galactic chemical evolution, but because they're dominated by short-lived uranium-235, it's not that big effect. Maybe we get like an extra billion year of degassing compared to planets formed later, right? And then we see the same kind of size effect, right? So we can map at, degassing lifetimes, both in terms of planet size, right? The kind of random variation in heat producing elements they might have, and also these galactic chemical evolution trends, right? And with that, right, we can finally do our kind of main punchline, right, of this part, right, which was trying to map out how old can a planet be today and still be actively degassing, right? And again, we're kind of taking the idea that this active degassing is probably important for driving the kinds of geochemical cycling we think might be necessary for climate regulation and habitability, right? So, we took all these results I just showed, right, and calculated, how old can a planet be and still be actively degassing today, right? So we did that with two different limits. One is the average, right, so the middle of our degassing lifetime distributions. And then to be a little more optimistic, we looked at the upper end, the upper 95% confidence level, right? So the planets that kind of luck into getting lots of heat-producing elements, right? And then we mapped real exoplanets on here for planets that we think are rocky, and planets that at least have ages, right? And so there's actually not that many planets that have at least some reasonably measured age and also have some density information that can give us ideas that they're hopefully at least, predominantly rocky, right? But we tried to find all the ones we could and put them on this plot, right? And the basic punchline here is, so this line is this maximum age a planet can be, right? And still be volcanically active today, assuming stagnant lid tectonics, right, like we assumed here, and also assuming, I wanted to make these estimates conservative. So all the assumptions I made in the model led to planets cooling off kind of as quickly as reasonably possible. So you should think of these predictions as sort of the floor, like the kind of minimum lifetime that degassing could last, right? Right, so actually this age max is not so old, right? So it might only be a few billion years old to maybe, if we're a little optimistic, up to 5 or 6 billion years old, depending on planet mass, right? And so, there are a few planets that plot up in this part of the diagram, which are planets we would be pretty confident could still be outgassing today. But there are lots of planets that are pretty old, including the TRAPPIST system, actually, right? Which plot down here in the range where, we can't be so confident that they might still be outgassing today, right? And I think that's kind of the way to read this diagram is planets up here, right? We can be reasonably confident, have a good chance to still be volcanically active today. Planets down here, right? I'm not saying for sure they're geologically dead and volcanically dead, but we certainly can't take it for granted, right? And in order to be still volcanically active, they might need other heat sources like tidal heating, right? Or maybe having plate tectonics, if they do have plate tectonics, might be a way for them to stay volcanically active longer, right? So I think this is really interesting for when we start looking at atmospheric information about the TRAPPIST system, to see if we see any signs of volcanic activity on those planets still, or whether they might be dead by now, because they are pretty old. The kind of median age here is 8 billion years old, so significantly older than our solar system. Yep. Okay, actually, so Francis, how am I doing on time? Do you want me to wrap up in a couple minutes, or?
Yeah, you have about 10 minutes to the top of the hour.
Okay.
Yeah, maybe 5 minutes.
Okay, yeah. Okay, I think I can wrap this up quickly. This is just a short little kind of last part. Right, so the last part was to switch gears and talk about whether exposed land, so like kind of major continents, is important for driving the same kind of climate regulation through the carbonate silicate cycle, right? So basically what happens if we have planets that maybe don't form continents, or they have enough water to bury the surface, right? And I want to be clear that for this, we're going to look at planets that have like only like the surface is only covered by say a small amount of water, right? So I'm not thinking about planets that have hundreds of kilometers or thousands of kilometer thick oceans, right? Earth, but just a little bit more water to flood the surface. Right, so this really comes down to thinking about how the silicate weathering feedback works, right? So if we write out typical ideas or parameterizations for how the silicate weathering flux, so the rate of CO2 removal from the atmosphere, depends on climate conditions, right? Like temperature and atmospheric CO2, right? There's ideas that it depends on temperature, both from the way silicate weathering reactions run faster at higher temperatures, and also from higher rates of rainfall as the climate warms, that leads to higher weathering rates, right? And there's also ideas that at least before land plants became widespread across the planet, right, that the silicate weathering flux might also depend directly on atmospheric CO2, right? With atmospheric CO2 essentially setting like the pH or acidity of rainwater, right? More CO2 should mean more in the atmosphere should be more dissolved in rainwater, right? And this can also boost silicate weathering rates. Right? Right, and so it turns out that the way this feedback works, right, actually depends a lot on this kind of relative breakdown between how strongly temperature dependent or directly atmospheric CO2 dependent the weathering rate is, right? And there's been a lot of nice recent work developing similar parameterizations for seafloor weathering, right? Both from observational constraints, looking at like drill cores in the seafloor, and also from models that take, model equations like this and try to match proxy data going back in time, right? And try to work out some of these parameters like this activation energies kind of controlling the temperature dependence and this beta exponent that's controlling the CO2 dependence, right? And from some of the most up-to-date work on this, right, we used work from Josh Chrysanthemum-Totten, right? The finding is that actually for seafloor weathering, so weathering of just the rocks under the water rather than weathering on land, right? This temperature dependence actually looks to be pretty strong, right? And the direct dependence on CO2 in the atmosphere, because it's sort of modulated by how that affects the pH of the ocean, seems to be pretty small, right? And that's actually really good for climate stabilization, right? For a planet being able to regulate its climate as a function of changing solar luminosity, right? And we can see that really by just looking at the basic equations here, right? So over long time scales, right, the weathering flux, right, works to always kind of adjust itself to balance out what volcanic degassing is doing, right, as long as we don't hit something like this supply limit of weathering like I was talking about earlier, right? So if we think about the system always trying to go to this steady state between weathering and degassing, right, then if we imagine, say, dropping the solar luminosity, right, like we moved Earth outwards or something like that, that's going to drop the temperature, right? So CO2's got to build up in the atmosphere until this weathering flux can now, again, rebalance the same degassing flux, right? And so if the temperature dependence and direct CO2 dependence are both strong, right, then as CO2 is increasing in the atmosphere, this is increasing and this is increasing, right? And we'll actually reach a new steady state after this hypothetical example of pushing the Earth farther out in the solar system at actually a lower temperature than we had before, right? If this CO2 dependence is really weak or maybe gone, right, then the only way to rebalance the system is to bring the temperature back up to exactly where it was before, right? So a weak CO2 dependence and strong temperature dependence is actually the best way to have really good climate regulation as the solar luminosity changes, right? So Ben played with this idea in some simple models of the carbonate silicate cycle using these parameterizations from Chrysanthemum-Totten's work, right, and found basically what we expect here. So this is the temperature as a function of solar luminosity, again, normalized to the Earth, for planets with different ocean coverages, right, going from very little oceans up to a completely ocean-covered planet, right? And you can see that the completely ocean-covered planet, right, actually regulates its climate better, right, as a result of these different parameterizations than planets that have a significant amount of exposed land. Right, we also looked at this as a function of changing the CO2 outgassing flux, right? And there things actually work the other way. The ocean-covered planet is a little less responsive, right? So it actually doesn't regulate its climate as well as a planet with more exposed land because we're essentially kind of weakening the feedback in that way, right? But if we actually put both of these together, right, like this map, which is kind of similar to one of the figures I showed earlier in the paper from a different, earlier in the talk from a different paper, right? We've got solar luminosity normalized to the present-day Earth on the x-axis and outgassing rate normalized present-day Earth on the y-axis, right, and map out where we get climates warmer than freezing, right? So that's the red, anything above this black line, right? Compared a water world planet with 100% ocean coverage versus an Earth-like planet, right? We see actually the water world planet has a larger region that can remain habitable, right, or above freezing at least, than the Earth-like planet, right? Mainly this kind of set of the parameter space, right, would lead to frozen climates on an Earth-like planet, but actually lead to still temperate above freezing climates on a water world planet, right? And it's entirely due to this different kind of behavior of seafloor weathering versus continental weathering. All right, so I will wrap it up there. So there's time for a few questions, right? And just summarize here with, if we argue that planets that do not need plate tectonics to have a carbonate silicate cycle, these same kind of feedbacks can happen on planets with stagnant lids. But the lifetime of volcanism on these planets is really important for driving this geochemical cycling. So we looked at how long volcanic activity can potentially last on planets by constraining heat-producing element budgets from what we can infer from stars, right? And found, at least for very conservative assumptions of how thermal evolution works, we might only have 2 to 4 to maybe up to 5 or 6 billion years of volcanic lifetime on planets, depending on their size and other kind of factors, right? And then last here, we talked a little bit about aquaplanets, planets that don't have exposed land, and whether they can stabilize their climate. And in fact, not only does it look like they might be able to, they might even, in some ways, act even better than planets that do have exposed land, at least just in terms of climate stabilization. There might be other astrobiological things that those planets are missing. All right, so thanks, and I'll stop there.